All right, so I'm going to start with, I just have a bunch of notes that I'm going to go over with you guys first, and then open up to specific questions. I know there's stuff about like the lenses and mirrors, so I'll cover that too. But the emphasis for now will be just this kind of general overview, chapter by chapter. And once again, when I get to the end, anything I left out, additional problems, throw them at me. We'll just tackle them one at a time. I will try and occasionally make sure, because I'm going to be focusing on my tablet that I'm writing on. I'll try to make sure that I keep focusing on the chat, but if anyone sees that I've missed a couple of chat questions, I'd appreciate you just unmute yourself and just say, flag me down. So let's get started, all right? So, whoa, all the way back to the beginning. I'm labeled these by chapters relative to the book instead of the modules or sections, just chapters in the book, right? And this is basically electricity, our introduction. So let's start writing down concepts. The fundamental unit of charge, right? I label it with a lowercase q, and it is 1.6 times 10 to the negative 19th coulombs, right? Often you'll find this labeled as QE or E or are also used to denote this unit. And things to know. So electron has negative 1.6 10 to the negative 19th Coulomb charge. Proton has positive Q charge. So given a charge, we can associate Coulomb's law, which is the force between charged objects. So that force goes as K, Q1, Q2, R squared. Let's put some pictures to this. Let's say I've got a minus charge here and a positive charge here, right? This will be an example of an attractive force, right? I call this charge 1, charge 2, just for the notation schemes. Then this guy is producing a force, F. 2 on 1 is how I like to call it. Newton's law, or third law, you could say, look, there's also a equal and opposite. Make it a little bit longer. 1 on 2. And let's go through these terms. Charge of one, charge of the other, Coulomb's constant. .99 times 10 to the 9th. Make sure I get my units right. It'll be a Newton meter squared per Coulomb squared. All right, so right. So emphasis. While in this linear, just straight line case, it's kind of obvious. R is just the distance separating these two charges. When we go to advancing it, go to the vector problems, and yes, I'll do some examples of those. The R isn't just the horizontal or vertical, it's the radial distance between the charges. Right. What else? Let's see here. We talked about, we introduce epsilon naught. That is that electric let's make that actually a legible word. Electric permittivity or permittivity constant. And this comes up, is that high enough for you to know? All right. So I'll squeeze in these margins here. So this epsilon naught was this, you can think of it as the electric constant. In fact, you can use this relationship. K is 1 divided by 4 pi epsilon naught. Always useful to like have these values written down. So like I have a little cheat sheet because a lot of these I don't remember. Like, don't waste my time. But numbers wise, 8.85, 10 to the minus 12th. That is a Coulomb squared per Newton meter squared. Right. Next on our list, the electric field, right? Its units is newtons per coulomb or volt per meter. Identical, those are equivalent. And it comes from this concept that E is defined as the force per unit charge, right? Now the expression that we'll use frequently is that F is QE, right? Basically this says that given an electric field, you can find the force on a charge inside that electric field. Oop, let's get you in. Right. And our simplest example, the positive charge, right? Positive charge, it's going to have electric fields that go radially outwards. And electric field of this charge is given as 4 pi epsilon naught, 1 over that, Q over R squared. All right, guys, I'm going to scroll up. Did I make a mistake earlier? No, I didn't. All right. I always want to make sure that I don't get the squareds wrong because that's a common mistake. And yes, forces go as 1 over R squareds. Electric field also goes as 1 over R squared. So, anything else I want to say in chapter 17 specifically? Right now, we're just conceptual overview. So let's keep going on. Chapter 18. Energy, work, potential. All right, those are those concepts. Big one. The work to go from A to B is the minus change in potential energy. Right. It's gotta be specific, that's why I'm writing this out. We could say, take these two charges. We've calculated the forces between them. We could say how much energy is stored there. And that energy is 1 over 4 pi epsilon naught Q1, Q2 over R, right? So it's no longer squared, all right? It's just 1 over R. It looks identical to, say, Coulomb's law because they're related. We could find electric potential, right? So the thing is the electric field, it was defined as the energy per unit charge, which we want the useful equations, useful expressions. We'd say, look, the energy of a charge inside some potential, right? How much energy does it have? There's your answer. So some facts as a reminder. If I give you just the electric potential, I would say positive charges, they tend towards, they're going to move towards the high potential. Negative charge, right. This saying high electric potential is like saying there's a lot of positive charge there, right? There's a large concentration of positive charge. All right, keep moving on. Right. The parallel plates capacitor. So we all love this one. We'll have two plates separated by some distance d, and it'll create a uniform electric field across it. And one way to do this, take two plates, you stick a battery on it, and there's the voltage that's providing the potential difference. Some things we can say. Well, we can say that the electric field for, I'm going to use dash dash to represent parallel, right, is minus V. Well, let's go for magnitude. I'm not going to worry about the details of the directions here, so I'll go for magnitude. Right. The electric field inside parallel plate capacitor going to be given as the potential over the separation distance. Right. And while we're on topic of capacitors, we can say, look, capacitance. That was this geometric idea. We say, toy around with the shapes of what I have, the distance, how big my object is, and say, well, how much energy can we store there? Right. Q is the charge on plates, and V is the potential across them.
Professor, you have a question in chat.
Yep, saw it. So Q is the charge on plates. V is the potential across the plates. Right. Just go back. Okay, I think we're caught up. So circuits, we use, here's our capacitor symbol, equal bar lengths for a capacitor. And we had 2 ways of sticking them together. Let's see here. For series, we'd say 1, 2, 3. C1, C2, C3. Right? This is the opposite of the way the resistors add up. Right? Capacitors are opposite of the way the resistors. So C equivalent would be C1, C2, C3, all to -1. Whereas parallel, our example would be something like and then the capacitors in parallel, they can just to add up. All right. Right. Let's keep the strain rolling. If I scroll too fast, just yell at me to come back. There. All right, 19. We start getting into current, resistance, Ohm's law. All right. So definition. What do I mean by current? We're saying charge is moved. All right. Or changed in time. I have some buildup of charge here, and it scroll away. It goes somewhere else. Next. Where am I at in my notes? Big one for us. Basically, the only circuit type that we studied is anything that was Ohm's law, and that was said V is IR, right? V in volts, I in amps, R in ohms. Voltage, current, resistance. Right. Related to that, we found power dissipated by electronics. So P is the power, the rate that you're burning off energy. The way I like to think of power, pick up your cell phone or your laptop when, like, let's say you're streaming a lot of content, or you play video games, you're playing games on your device, and it just heats up a lot, right? There's a lot of energy being consumed, and it's got to go somewhere. And so for electronics, that tends to heat up the device. Oh, your P equals a voltage across the thing. times the current. So you'll notice that your laptops get hotter when you're doing a lot of things. You have a million tabs open in your web browser, you're streaming content. Like you'll notice that basically the current demand goes up, power starts to go up, and you feel the device get hotter. Right. So now we'll get to our resistors. So once again, we have them in series. R1, R2, R3. I'd say the equivalent is just the sum. When we'd use P equals I squared R. All right, so this is equivalent to that, I squared R. And let's box this in. Oftentimes the question is, should I use this one or this one, and how do I know? And the way to figure out is what is constant in your circuit. If what the stereotypical example is like, this circuit consumes this much wattage, and then I take the 2 ohm resistor and I switch it out. There's nothing, I replace it. Right? So you know the resistance is changed. So bad example because current and resistance changes. Let's do an example. Let's make up an example on the spot. Let's say here's my circuit. Nice and simple. 10 volts, 5 ohms, right? Current in this guy is going to be, let's see here, 2 amps. All right, power. Well, everything's equivalent. I can use whatever parts I want. So I would say, I'll just go with the easy one. I'll say V times I, and I'll get 20 watts consumed. Right. Then, okay, let's replace the resistor. Let's change it. And we'll call this 10 ohms. I've doubled the resistance. Still the same guy. Well, all right, the current has to change. Current change, so I prime would now be 1 amp. Could go back to my previous expression. So I would still use P equals V times I prime. If we change the battery instead, though, right? If we change the battery, then I'd say, look, P is I prime R squared, or getting this backwards, hold on. Square that times R. So there isn't a general case of one equation is the correct one to use. So you have to just look at the circuit you're applying and do what I do. Draw a picture, P, I, V, and just write them out. Give them prime notations. That's another trick that I highly recommend. You know, prime the notations, and you say which ones are consistent, which ones am I allowed to plug in? Because, like I said before, the equations are equivalent. They are the same thing. It's just one might be more useful than the other in that time.
What is the ohms on that resistor towards the left?
10 ohms. So
Okay.
yeah, to finish the example, this one would now be what? 10 volts. It became 1 amp. So this became 10 watts. All right. So I'm going to shift away from this now. All right, back to resistors. So in series, right, versus in parallel. R1, R2, R3. Excuse me. And then you have that weird sum of inverses guy.
Hey, Professor.
Mhm.
Would that be 1 over R equals 1 over R1 plus 1
Yes,
over R2?
yes. If you prefer it right in this way. Right. Right. Hold on a second. Okay. Let me write this one out explicitly. Right. Let's say this is my circuit. Let's say this is 2 ohms, 3 ohms, 6 ohms, right? And I want to say this is equal to just R equivalent. So R equivalent is equal to 1 over 2, 1 over 3, 1 over 6, 1 over all that nonsense. So let's see here. I cheated. I made them all factor into 6 easily. So what? 1/2 multiplied by 3. So this is 3/6, 2/6, 1/6, all over 1. 3 plus 2 plus 1. 3 plus 2 is 5. 5 plus 1 is 6. So this is 1 over 6 divided by 6. Well, fancy that. I got a nice single 1 ohm. Good point. Good point. All right. So I'll scroll up here. Another common way to write this. That'll get you the same result. All right, that's equivalent. All right. So keep going down. All right. Chapter 20, magnetism. All right, so simplest example, bar magnet. The magnetic fields exit the North Pole and come around back to the south. All right. That's really crucial for us. All right. Right. leaves North Pole. And returns to the South Pole. So fun fact, Earth's geometric poles, right? We've got our north and south geometric poles, and we have our magnetic poles. They're opposites of each other's. Like, so here's my model of Earth, right? And if you get yourself a little compass here, right? Let me scroll in a little bit. Get yourself a compass. All right. North, south. Whereas if I go over here, north, south. All right. So a compass is another magnet, right? So here's the point I'm trying to get at. All right. North poles. Do they attract or repel to other north poles? All right, repel. So what this tells us is that Earth's field magnetic north, magnetic south. So I'll draw a picture over here. So if you look at Earth's magnetic fields, you actually see something that looks, let's make that a little bit clearer. All right, so you get this silly thing where, right, this is a magnetic south, but it's our North Pole. And that's what I mean by the opposite, because of how our compasses are attracted to the poles of Earth. Right. All right, so let's start doing some expressions, some reminders of equations on this stuff. Yes, we will talk about that. In fact, it's literally the next thing in my notes. So let's get there. Let's see here. Force on a moving charge, right? F is Q V B sine phi. The angles are always going to be 90 degrees, guys. We always make the angles nice and 90 degrees, but I put it there for completeness, right? Right. Your direction by right hand rules. So let's give ourselves positive charge. Let's send it flying off that direction to the right. So there's its velocity. All right, I just noticed a question to Janelle's. Back to the Earth stuff. Sorry, guys. Yes, Earth's poles. It's a magnetic south, or sorry, backwards. Get myself mixed up. Our geometric south pole, Earth's geometric south pole, is in fact a magnetic north pole. Our geometric north pole is a magnetic south pole. All right, so let's go back to this guy. So let's say there's some uniform magnetic field like this. All right, what's the direction that this charge is going to feel a force on it? All right, so the right-hand rule that I adopted that I like to use and is the force is thumb. The velocity is your index. And the magnetic field is your middle, right? Yes, there are lots of other ways to do this. I'm going to stick to this one as always. And if you're uncertain, ask and we'll do other versions, right? So force on this charge. I'm going to do velocity. I see magnetic field coming up. I'll see a force coming out of the page. See that in purple. So I find it often helps to do a 3D depiction of this. So this is going to be the exact same picture, guys. Let's get those colors consistent. Right. The force here okay. Right. Okay, so related to this one, right? Relay expression is the force on the current wire, current carrying wire. And that one goes as F I L B sine phi. So current, length of wire, that's what the L is. All right. Magnetic field and the force. So let's do this one. Let's say here's my current of wire, right? And it is, let's try to do some numbers off the top of our heads. Let's say it's 10 centimeters long. Current is 2 amps, nice strong. And let's do a magnetic field. We'll say magnetic field is going into the page. Right. I'm calling it B external because I'm not talking about the magnetic field that wire produces. I'm only talking about some external magnetic field. We're not talking. And we'll say this one is 5 Tesla. Yeah, disclaimer. This is not the wires field. We'll get to that later, a little bit later. And so let's calculate the force on this wire. So here, I think, well, I made this one pretty just straightforward plug and chug, which is okay, but we'll do a right-hand rule to get the direction as well. So this would be 2 amps, 10 centimeters or 0.1 meters times 5 Tesla, right? 2 amps times 5 is 10 divided by times 0.1. I promise I did not stage this, but I did pick the numbers to work out to be exactly 1 Newton. Double check myself, make sure I'm not going crazy. Right, but direction. Direction of force. Here, I'll write the expression again. F equals I LB. There's your thumb, your index, and your middle finger. So over this one, right? I've got current going to the right. I've got a magnetic field. Crosses are magnetic fields going into the page. There's my magnetic field. So this wire would feel a force upwards. Right, the cyclotron. Right. Cyclotron motion. So our stereotypical example is some positive charge flies into this magnetic field. Right. So first thing to do is its trajectory. It's going to do some sort of circular path. Right. Yep. So this guy is going to come in and do some circle. Right. We're doing directional. When do we flip our thumb? Negative charges, right? So this is a good opportunity for that. If I shoot in a negative charge, negative charge, velocity, direction of field, force is up. But because it's a negative charge, gotta flip things over. So this one would do something like this. And that'd be its corresponding radius. Right. So how to get the radius? I know everyone's probably got that formula memorized, which is okay. Like that's fine. But I always like to go over from the principles, right?
So protons will always follow the path where the circle curves up, and electrons will always curve downward.
For a field pointing into the page, if I do this, if I have magnetic field coming out, then what will my proton do? My proton will come in, right? Velocity, Magnetic field up. All right. So then it would curve downwards, whereas my electron would come in. So to the right, magnetic field up, negative charge, flip that sign. So this guy would do that. So we have to just be careful and just be diligent. Say direction of current, direction the charge is moving, direction of the magnetic field, force. And like sometimes you'll know the force, but not like the magnetic field or something like that. That's a common problem. And what I find is me personally, I go current, I guess the magnetic field direction, see if I get the correct force. If that didn't work, well, do that awkward game of putzing around until you get your hand to line up with the diagram. I'm back. All right, so how do you get that raised to cyclotron motion? So when you're doing circular orbit, right, F is equal to the force on this guy. Well, force is QVB, right? F is mass times acceleration. Second law. You need to remember this one, guys. We use the second law forever. All right. And we can say for centripetal acceleration, right? V squared over R. Let's rephrase that. For circular orbits, you get M is V squared over R. Right? So charge is doing circular orbits. What do you find? You find that mass times acceleration is QVB. All right, so I'm going through this quickly. Yell at me if I should slow down. All right, and V squared over R is QVB. Solve for the radius. All right, multiply that across, divide. I get an MV over QB. All right. No questions here, so I'm gonna keep pushing on. Let's see here. We talk about the magnetic field of a current carrying wire. So go back to this guy. Here's my current. And you say, what is that magnetic field? Right-hand rule, the I like to use here is the grabbing the wire. Like literally, like take your pen and say, have the pen point in the direction of current, and then you grab it. Your thumb in the direction of your pen. And you're like, all right, I've got it. And I am going to curl this way. And that curling tells you which way the magnetic field is curling around. So for this guy, it'd be And so the expression for that is mu naught I over 2 pi r, right? What is r here? Distance from the wire. It's how far away from the wire you are, not the gauge, the thickness of the wire. Right. Right. Mu naught is the magnetic constant. Specific name is magnetic permeability constant. Right. The magnetic permeability constant. It's got an easy definition. It is 4 pi times 10 to the minus 7th. Let's see here. This is Tesla meters per amp. All right. And then we have our solenoids, all right? Think of as current loops is another way think of a solenoid. So if I sense a current going in like this, what is the direction of the magnetic field with this solenoid? Right, comes out of the page on top into the page at bottom. So that is a magnetic field. Yeah, let's not be fancy. Let's just right. So the solenoid needs some space. The solenoid goes as mu naught N over L I. In its number of turns, L equals length of solenoid. Most common way that you'll see this expression written is mu naught little n I. And n is just, the little n is just the ratio n over L. Right. Whew. Meters. It's the physical length of but I know, I see, sorry. L is in, wait about length or inductance. Good question. We'll get there. So yes, there is a inductance related to this. So gotta be careful for our notation. Here I'm saying L for length for now. And we'll get to the inductance in my next page. Right. Chapter 21. Induction. Right. Key law, all right. Faraday's law. All right. The induced voltage is the change in magnetic flux over change in time, right? Voltage, flux, B dot A. And since we're on the topic of solenoids, I'll just skip ahead and go to that. All right. Inductors, they are the same thing as solenoids. They are identical. Historical context, why we have the different names. All right. So you can say, all right, here is my inductor. Right. It'll have some level of self-inductance. Right. Right. And you can say E goes as L delta I delta T. All right. New equation. It comes from Faraday's law. It is a direct result of Faraday's law, but we're glossing over the details of how to get there. Right. So L, this is the inductance. Units of L is a Henry. This is voltage, current, and time. So context, 1 Henry is equal to 1 volt second amp. And there is like 1,000 other ways to write that equivalently. Go away. So use of this, all right? We can say, hey, what's the direction of these induced currents, okay? The shortest way to say this is that the induced field opposes changing flux. That's the shortest way to say this. Let's have some examples, right? I'll have a loop, and I'll drop the north end of a magnet towards it, right? All right, so what's going to happen? There is flux going through this guy. And then go to just a small second later. Well, that magnet is significantly closer. So the field density goes up. Right? So, conclusion. Right. Phi B is increasing. Magnetic flux is going up. The induced field points opposite the external field. And let's put some arrows on these. Right. Scrub a little bit, I'll try to keep them on screen. So this guy needs to create a field that does this. The induce. And now we can use our right-hand rules to get the direction of that current. There's the direction of the induced current for that case. Chapter 23. Electromagnetism, right? Just EM waves. Takeaways from this chapter, right? Speed of light is square root epsilon mu naught over 1. And for our purposes, 3 times 10 to the 8 meters per second. Universal speed limit, constant, always constant. Cannot go faster than that speed of light. And electromagnetic waves will travel that speed unless in medium. Once you try going through water or prism, like, you slow down. So right, you say, look, there's this index of refraction V medium. Inside index of refraction equals where V means the speed of the light inside that medium. Let's see here. What am I glossing over? Let's see here. V is equal to lambda F, wavelength, frequency, speed. All right. Right. Oh, glossed over one. E equals CB. The electric field is related to the magnetic field.
Professor, could you scroll up a little bit?
Yep. I'll take a little pause. All right. Snack break over. I'll hold on a second. I haven't been given the clear to scroll yet. Let's see. Snell's law. Then I'll get to those ray optics I was asked about at the beginning. Right. I'll move on. Shout me if I need to go back. Right. So Snell's law. Right. N1 sine theta 1 is N2 sine theta 2. Super powerful law. You're gonna need to use this one. I can just be a blanket statement. You'll need to use this. So let's do some examples. Actually, this will be a really good one. Right. Let me pull up the proper picture that I want so I don't screw it up live.
Professor, could you scroll over just a tad bit?
That good?
Yes, sir. That's perfect.
All right. So the game of I shoot the ray in through the blocks, and how do we compare the corresponding index refractions? This one's tricky, so I just want to go over it with everyone live, and we can see like the different versions of this. So let's do it this way. I send in my ray like so. Let's get the ruler out. Let's make this a bit more accurate. Let's say I come in at 20 degrees. Right? And then move all these guys down. Come on. Come on. All right. It's 20 degrees, and then I'll refract it out. Let's do 30 degrees. I'm putting numbers to it to try and help. Right. So that's 30 degrees. All right. We do some quick geometry arguments. That's also 30 degrees. Let's have it bend in. Let's have it go to like 5 degrees. Five degrees. Also 5 degrees. And then we'll just bend way out. Right. And 1, and 2, and 3. Which one's the greatest index refraction? So, right. Let's start doing some comparisons. Right. Here's the trick. Right. The trick is that the indexes are going to be opposite the angles and vice versa. So if I say 30 degrees, well, that's going to be greater than 5 degrees. And the notation that I've been used is that theta 1 is greater than theta 2. Therefore, the indexes flip. I would say N1 is less than N2. And then repeat. Go to the second boundary. 5 degrees is less than 60 degrees. 5 degrees is less than 60 degrees. I'd say theta 2 is less than theta 3. Theta 2 is less than theta 3. So N2 is less than N3. So what we've set up so far, we know N1 is less than N2, N2 is less than N3. So we know N2 is the smallest. How do N1 and N3 compare? Right. Well, here's a trick. Apply Snell's law. N1 sine theta 1 is N2 sine theta 2. And the second boundary, N2 sine theta 2 is equal to N3 sine theta 3. N2 sine theta 2. N2 sine theta 2. Why is N2 not greater than N3? Because I messed up. Good catch. Yes, you do always flip it. Yes. So let's scroll back. Let's go back to up here. So it's here. 5 degrees is less than 60 degrees. Yes. Thank you for catching that, guys. Yes, you do always flip it. All right. Always flip that relationship. That's the goal here. So then let's go round 2 on this analysis. What do we got? We know N1's less than N2. And we know that N2 is greater than N3, so we know N1 has to be. I gotta say this carefully, my words, so I want to get this correct. N2 is greater than N3, which is equivalent to saying N3 is less than N2. Doesn't help me figure out how N1 and N3 are related. All right. Let's see if I can do that logic here. N1 has to be smaller than N2. N3 is smaller than N2. How? So with this, you have enough information to say, next. Is the largest in this drawing. Like, you got to be very careful with your rays that you draw on the angles. Right. So now let's figure out the relationship for N1 and N3. Right. How to relate N1 and N3. So N1, sine theta 1 is N2 sine theta 2. And Snell's on the other side. N2 sine theta 2 is N3 sine theta 3. So we can cut out the middle guy and say N1 sine theta 1 is N3 sine theta 3. Basically, it's as if the middle block isn't even there for the purposes of these angle calculations. Right? So what do we say? What? Theta 1 was 30 degrees. Theta 3 was, let's go back a bit, 60 degrees. So theta 1 is less than theta 3. Flip it. N1 is going to be greater than N3. So altogether it becomes, let's see here, N3 is at the bottom, N1, N3. for that picture. All right. Thank you. All right. So try not to go too far away. All right. Chapter 24. Geometric optics. All right. Sines, right? Rays, right? Let's go through this. All the equations we need. Y prime over Y equals minus S prime over S. And 1 over S, 1 over S prime. But what about the sines? What about the sines? I know that's the huge question, right? So, rules, right? Let's see here. Yep. Concave mirrors and converging lenses have positive F. Focal length for the mirror and the converging lens. F is positive for those guys. All right, and that's, take that as like a definition, mathematical definition. Right. Convex mirror and diverging lenses have negative focal lengths. All right, and in all these pictures, we imagine the rays are coming from over here.
Hey, Professor?
Yeah.
I thought concave went with diverging and convex went with converging.
Let's see here. Concave, you cave inwards. I'm just doing a little scribbling to convince myself. Yep, so that's a real image. All right, where's this one? Yep, that's the virtual image. Can you repeat the question?
I thought, okay, so you say that the convex lens is the diverging, convex and diverging are the same?
Not the same. They have negative focal lengths.
Well, but they go together is what I mean. For some reason in my notes, I have concave going with diverging and convex going with converging.
Concave. I'm not certain. I'm not certain about your notes. Here, like we'll go through the pictures and we'll convince ourselves. So. Right. Right. So we'll work out some examples and hopefully we'll clear that up. The emphasis here, right? Positive focal lengths up here, negative focal lengths down there. That's the emphasis. Right. So now the question is, generate some images, right? When is S prime positive or negative? So, right, S. Right, you have some real object at some physical distance away from the object. S is basically defining what positive ray traveling direction is. F depends on optical object. S prime is positive if image is real. Rays cross. And S prime is negative if the image is virtual. So there are your rules. I'll try and hold on for just a little bit. And I'll just do a quick example with every object to convince you. So let's do the concave mirror. Let's make that a little bit bigger. Right. And let's put the object here. Right. Shoot my rays in, see where they go. So I'm going to use different colors to represent different rays. I'll do one principal ray parallel to the optical axis. Reflect that through the focal points. Next one. I'll have this one go through the focal point. It comes out parallel. Right. Emphasis. The outgoing rays cross. That's what I mean. That's a real image. S prime is greater than 0, positive. Let's do our next one. I next claimed that the converging lens would be positive. Everyone okay if I scroll this image off the screen? All right. Trying to go too far off. So here's my converging lens. I'll put my object here. All right, same game. Shoot in parallel. Instead of reflecting, now we refract. No, I don't ask you guys to draw the rays. I feel like you didn't have enough time with the material to do that. But I am drawing the rays for you, so you have these pictures in your head. I forget if it's in the notes or one of the practice solutions, but there's like a diagram of like different optical objects, different positions for the object, and the resulting where the image is. Great thing to have on your like your cheat sheets. Like that's a great thing to have. I don't want to force you to draw these pencil rays because, like I said, we just didn't have enough time in the material. But all right, continue on. So I claim this will be a real image. So what do I mean by real image? Oh, need a different color. All right, this way went through that focal length, so therefore it comes out nice and parallel. And boom, all right. Rays physically cross. There's a real image being generated. All right, keep up the train. Now we're on the this is the convex mirror. The way I remember the convex mirrors, 7-Eleven, go to any store or a gas station, whatever, and you always see those domed mirrors hanging in the ceiling. And look in the dome mirror, and you can basically see everything around you in the convenience store. That's a convex mirror. No, mirror only has the one focal length, and it's inside the mirror. So let's have our object out here. Look at this. Send a ray in. It reflects this way. So there's my outgoing ray. I'll do another one. This one is the vertex and bounces off. All right. Those are the outgoing rays. Right. Don't cross. We still see an image, but it's not a real image. What we see instead is a virtual image. And for reference, S prime would be negative in that case. Other ways to say this: image is behind the mirror. All right. And we'll do our last one for completeness. Have my object here. And yes, I'm powering through this quickly. Like I said, I just want to get to the pictures. That's what matters. So this guy, just like that. There's my outgoing ray. I don't want to do this one. This one. If you're aimed at the far one, you come out nice and straight. And once again, outgoing rays don't cross, so you trace them behind the lens. And there's your virtual image again. Great example of this. Does anyone have a reading lens? And I don't mean glasses you put on specifically for reading, but it's a lens that you put like on top of the block of text to like magnify it. That'd be an example of this. Alrighty. Whew. Yes, I did reach to someone. They believe me. This is real sci. This is real physics. Alrighty. We're at like the hour-and-a-half mark. I will keep things going for specific questions, but otherwise, I'm done. Like I said, your tests will open tonight. You still have the what till Thursday night to complete it, and I'll happily answer questions for you guys. I know this material stuff, and I'm not out to like leave you hanging. No, I will not be me. I will not require you to do drawings on the final. I know it was awkward in the homework, and quite frankly, you just didn't have enough time and material. It would not be fair in my assessment. Oh, great point. Great point. So let's do this one again. I like the dome mirrors. We all miss going to our convenience stores. All right. So, here is my object. All right. Object distance, and let's shoot our rays in so I get this right. All right, so it goes off like that. Do one off the vertex. Alrighty. And so we find this guy behind the mirror. So I'd say boom to boom, S prime, image distance, right? Well, we also can talk about the, let's do it in purple, Y and Y prime. Image height, or no, sorry, got that backwards. Y is the object height. Y prime is the image heights. So I think it's safe for me to say that I don't ask you to calculate image heights at all in the final. I'll save you a little bit of time. I can agree that quarantine is getting to us all. Yep. I'll stay on the line. I'll answer specific homework questions. As long as the questions keep coming, I'll stay here. All right. Mars is. Any questions? Well, there are 13 problems in the final. I'll post an email announcement about that too. But yeah, it's 13 problems. 2 of them will be long form written. All right. So I'm gonna start. I'm gonna go with the order these questions came in. All right. Diameter Mars is this big, so go away. Diameter Mars is this big. Earth is, Mars is at this distance. By a spherical concave telescope. All right, so here's Mars, here's its diameter. And I'm going to have a spherical, its minimum distance Earth is 5.58. Spherical concave telescope. So I'm going to have a concave telescope. Alrighty, so F is 1.7 meters. S is the distance, minimum distance, 5.58, 10 to the 7th kilometers. Find the diameter of the image of Mars formed by a spherical mirror. Alrighty, so let me think about this. M is minus y prime over y. And it's also equal to, well, it's also equal to minus s prime over s. It want to know is the height of the image. So question asks for y prime equals minus s prime over s times y. Right, we have y, it's the diameter of Mars. Right, need the image distance, need s prime. Well, you can say, look, 1 over s, 1 over s prime equals 1 over f. So if I'm not doing this too quickly, this is s times f over s minus f. Yeah. All right, so let's plug in those numbers. This is 5.58, 10 to the 7th kilometers. You need to put that in meters, so multiply by another 1,000. 10 to the 10th meters. Times 1.7 meters. All over 5.58 times 10 to the 10th meters. Minus 1.7 meters. It's about 1. Did I make a mistake? Let's see here. Shouldn't be about 1. Should be close to the focal length. Let's just do the math. Plug in the calculator. All right, so S is 5.58. The 10th, F equals 1.7. All right, S times F over S minus F should be about the focal length. Yeah, S prime is 1.7 tons of zeros, decimal places. So yeah. All right. So S prime, like, all good. It's 0, 0, 0, 0, 0. So on. 1, 2, 3, 4, 5, 6, 7, 8. 5. So in this case, we'll just say S prime is equal to 1.7 meters, or for the very far away objects, their images just form at the focal length. So now let's get the diameter. All right, diameter. Let's see here. The image height is going to be minus 1.7 meters over the object distance 5.58. Let's keep the units consistent. The diameter in the question was given to us as 6.794 kilometers. So 5.58 to the 7th kilometers times 6.794 kilometers. Divided by S times 6.794. That seems wrong to me. The image formed in this, because I'm getting 2.1 10 to the minus 7th meters. That seems off to me. What am I? Let me read that question again. The diameter of Mars is 7,000 kilometers. Its minimum distance is 5 times 10 to the 7 kilometers. And the diameter of the image of Mars formed by a spherical concave mirror. Kevin, no, you do not. I have to keep things equal between my online and my formally on campus, and proctors were not available for my on campus class. So you don't need to schedule a proctor, is the short answer. Sorry, coming back. Diameter of Mars is this. Yep, that's closer to the answer I was expecting. So good news, I'm only off by orders of magnitude. Bad news is, where did I go off? Up, I see it. That's in meters. So if I just convert that into meters as well. Unit error. Or let's see, that's 0.21 millimeters. Yep. Those pesky powers of 10, they always kill us. All right, so I saw another question. Section quiz 5, problem 1. Never mind, I figured it out. How similar is 2008 practice file to our final? Let me look at it. Let me look at that practice file. 2008. All right, so the question is, how does the 2008 practice test compare to our test? Too long. The 2018 test is about twice as long. Style questions. Yep, same style. A little bit too long. I can be blunt. I can say the one, that 2018 practice test, the solenoid, where you like find its inductance, that's not going to be on you. Full disclosure, this was the first time I'd ever given a final in 112. It's actually my first semester ever teaching, and I basically had to chuck that question out for that class, because like my policy is that like if if like 70% of a class gets a problem wrong, that's on me. Like I screwed up the problem, so, or didn't teach the class effectively. So and that happened with that solenoid problem. Number 17, yeah, that problem. I like it, but it's not a fair question for this level of material. Alrighty, so I'm feeling a bit of a lull, so I think I'll call it here. Thank you everyone for coming. I hope this was helpful, and like I said, email me if you got questions. I'll happily answer them, and be safe, guys. Like, yeah, this might be the last time I ever get to interact with you. So, be safe. If you can, enjoy the summer break. Yep, that's what I was going for. I know this was a wide range of material, and I'm hoping this helps condensed it down a little bit. So it depends if you're in my online or formally on-campus class. If you're an on-campus student, your lab grades should already be posted. If you're online, they'll be posted. Check my graders. They should be posted by like the end of the night. So short answer, tonight. So the last test will be on Thursday night. So Friday, like this Friday is the deadline basically for me to turn around and get those grades up. I will post grades to Blackboard first before Leo Online. That way everyone has a fair chance to say, hey, I think you calculated my grade wrong, or I think you missed this, or whatever. Like I want people to have the opportunity to just contact me and say, oh, this is missing. Like, so I posted to Blackboard, and then within about 24 hours, I posted to Leo just to try and give you that time to question or challenge me. Like, you're well within your rights to challenge the grade and ask me if that's correct. And I'm willing to work with you guys. Like, as much as my previous few emails might come off as me being a hard ass, I'm flexible. I'll gladly work with you guys. So. All right, okay, how to calculate the lab journals. Okay, that could. The homework journals. So basically, each journal was worth like 16 points. As long as you have a page of scratch work in there and like every file uploaded, you're gonna get full credit. I had a policy of like penalties for being late and penalties if you didn't do enough work, but with the pandemic, like that kind of stuff seemed cruel and unnecessary. So basically, if you uploaded something and it's a page of scratch work, you're going to get full credit on each of those journals. Will those be posted? Let's see here. Do I have graders for that? Is that on me? No. Lost my grader. So getting all those together is all back on me. That's okay. So by tomorrow night, you'll have all those uploaded. I'll shoot for tonight, but a man's got to eat and get back to work. Oh, please upload Scratchwork right now. Like if you upload Scratchwork now, I will give you credit. And like honestly, like just I'll be blunt, like I don't care if it's work that you just threw together right now. Just get something in there, and I will grant you credit for that because like, man, this world got crazy and weird. No curves. Let's see here. So yeah, no curves. It's just a raw point value across everything. Add up all the points. Extra credit gets added to your points. So like, great example. Homework has like 600 points. Between the journals and the extra credit and some homework problems, let's say you get like 650 points on the homework. You get those 50 points. That counts towards your total score. The attendance. So basically, all right, so attendance score, this doesn't apply if you were an online student at the start of the semester. Right. Right. It's either all right, it's either some of the section quiz scores or times what's the attendance score worth? It's worth like 600 points. Right. Where that was attendance before the shutdown. Double check that I got that value right. So